Good morning, everyone. My name is Angelina Ling Yun Eun from Option Science STKC. Today, I will present Mathematics in Science Task 2B. Today, I will present my report about simple pendulum investigation. In this presentation, I will explain the experiment, the data collected, and most importantly, how the value of G can be determined from the experimental data. The aim of this experiment was to determine the gravitational acceleration g using a simple pendulum. We also investigated the relationship between the length of the pendulum L and the square of the period t squared. According to the theory of simple harmonic motion, a longer pendulum has a longer period of oscillation. Therefore, by measuring the period for different pendulum lengths, we can determine the value of gravitational acceleration. The period of a simple pendulum is given by this equation. T equals to 2 times pi times square root L over G. By squaring both sides, we obtain T squared equals to 4 times pi squared times L over G. This equation has the same form as the straight line equation, so we can compare it with y equals to mx plus c, where y represents t squared, s represents L, and the gradient is 4 times pi squared over g. Therefore, after obtaining the gradients from the graph, we can calculate gravitational acceleration using g equals to 4 times pi squared over gradient. Since the intercept is 0, the theoretical graph should pass through the origin. The apparatus used include a rheostat, thread, plasticine bulb, stopwatch, meter ruler, protector, and G-clamp. Two different methods were used, which were 25 grams and 40 grams. The pendulum length was varied from 20 centimeters to 80 centimeters, while the oscillation angle was kept below 10 degrees to ensure simple harmonic motion. For each length, the time taken for 10 oscillations was measured twice and the average value was recorded. This slide shows the data collected using a 25-gram plasticine bulb. The length of the pendulum was varied from 20 cm to 80 cm, while the mass remained constant at 25 grams throughout the experiment. For each length, we measured the time taken for 10 complete oscillations twice, and the average time was calculated to improve the accuracy of the results. Then the period t was obtained by dividing the average time by 10, and t squared was calculated. The data is presented in three tables for easier reference. This slide shows the data collected using a 40-gram plasticine bulb. The procedure was the same as before, but the mass was changed from 25 grams to 40 grams. Now I will present the graphs and gradients obtained from our experiment. First, this is the graph of t squared against the pendulum length L using the 25-gram pendulum for lengths from 20 cm to 80 cm. The x-axis represents the pendulum length in meters, while the y-axis represents the square of the period in seconds squared. As we can see, the graph shows a straight line relationship indicating that t squared is directly proportional to L, which agrees with the theoretical equation. Since the theoretical equation has zero intercept, the best fit line is drawn through the origin. From the graph, the gradient is approximately 4 seconds squared per meter. Using the equation g equals to 4 times pi square divided by gradient, we substitute the gradient into the formula and obtain a value of approximately 9.87 meters per second squared. This value is very close to the accepted value of 9.81 meters per second squared, showing that our experimental result is accurate. Next, we calculate the gradients from both the GSP graph and the manual graph. The gradient values are very similar, showing that both methods produce consistent and reliable results. The following graphs use only the data from 20 cm to 50 cm and 50 m to 80 cm for the 25 pendulums. In both cases, the graph remain linear and the gradients are close to the period value. This shows that the relationship between t squared and L remains consistent throughout the experiment. We then repeat the experiment using a 40-gram pendulum for the full range of 20 cm to 80 cm as well as the 20 cm to 50 cm and 50 cm to 80 cm range. All the graphs again show the straight line relationship. The calculated gradients are very close to those obtained using a 25-gram pendulum, and the calculated values of G are also close to the accepted value. Overall, all the graphs show that 2 squared is directly proportional to the pendulum length while changing the mass from 25 grams to 40 grams, does not significantly affect the period of oscillation. Therefore, our experimental results are consistent with the theory of the simple pendulum. And this is the summary table for my result. Now I will explain the percentage error obtained from both the manual graphs and the GSP graph. The percentage error was calculated by comparing our experimental value of G with the accepted value of 9.81 meters per second squared. Using the formula shown on this slide, for the manual graph, the percentage errors range from 0.6% to 2.1%. For the GSP graph, the percentage error range from 0.6 to 1.1%. Overall, all the percentage error are below 3%, indicating that our experimental results are accurate and reliable. The GSP results have slightly smaller percentage errors, showing that they are slightly more precise than the manually plotted graphs. The small differences may be caused by human reaction time when using the stopwatch, slightly errors in measuring the pendulum length or air resistance during the experiment. Therefore, both the manual graphs and the GSP graphs produce value of G that are very close to the accepted value, showing that our experiment agrees well with the theoretical value. The experimental results agree well with the theory of the simple pendulum. Firstly, the graph of t squared against L is a straight line, showing that t squared is directly proportional to the pendulum length. Secondly, the calculated values of gravitational acceleration range from approximately 9.75 to 10.02 meters per second squared, with percentage errors between 0.6% and 2.1%. These values are very close to the accepted value of 9.81 meters per second squared, indicating that the experiment produced reliable and accurate results. In addition, both the 25-gram and 40-gram plasticine bulbs produce almost identical gradients and values of G. This confirms that the mass of the plasticine bulb does not affect the period of oscillation. Finally, the values obtained using GSP were slightly closer to the theoretical value because the software determines the best fit line more accurately than manual plotting. Although the experiment was successful, several sources of error may have affected the results. These include human reaction time when using the stopwatch, inaccurate measurements of the pendulum length, releasing the pendulum with an initial push, and the effects of air resistance and friction. To improve the accuracy of the experiment, an electronic timer can be used instead of a manual stopwatch. The pendulum length should be measured carefully from the pivot to the center of the bulb. The bulb should also be released gently without applying any extra force, and the oscillation angle should always be kept below 10 degrees. In conclusion, the objective of this experiment was successfully achieved. The result shows that the square of the period is directly proportional to the length of the pendulum. The calculated value of gravitational acceleration was approximately 9.87 meters per second squared, which is very close to the accepted value of 9.81 meters per second squared. Therefore, the hypothesis is accepted and the experimental results are consistent with the theory of simple harmonic motion. Thank you for your attention.